Welcome back. In our last session, we mapped out the AI hierarchy, from artificial intelligence at the top down to large language models at the center. Today, we're moving beyond theory into the technical foundations that determine the cost, speed, and capability of every AI system you use. We're covering three critical concepts: tokens, context windows, and embeddings. As you can see on the slide, tokens are the atoms, the fundamental units of language processing that drive API costs and execution speed. Context windows are the memory, the bounding box of AI attention that dictates analytical capabilities and document scope. And embeddings are the meaning, the mathematical representation of language that unlocks semantic search and conceptual mapping. Let's start with tokens.
This slide gives you the big picture of our three topics at a glance. On the left, tokens, the fundamental units of language processing. They drive your API costs and execution speed. In the center, context windows, the bounding box of AI attention. They dictate what the model can analyze and how large a document it can handle. And on the right, embeddings, the mathematical representation of language. They unlock semantic search and conceptual mapping. Think of these three as the plumbing of every AI system. You might never see them directly, but they determine everything about performance, cost, and capability. Let's dig into each one, starting with tokens.
First, let's talk about tokens. Think of a token as a unit of language. LLMs don't read words like humans do. They process text in fragments. Look at the example on this slide. ChatGPT is powerful, gets broken into 7 tokens: chat, G, PT, is, power, full, and the exclamation mark. Short words might be 1 token, while long or complex words are broken into 2 or 3 pieces. The baseline rule of thumb is that 1 token equals roughly 3/4 of a word. So 1 page of about 500 words translates to roughly 650 tokens. Punctuation, numbers, and long words each break into their own individual fragments. The key takeaway here at the bottom of this slide says it perfectly. Tokens are the raw material the LLM breathes in and out. You pay for exactly what the machine breathes. Tokens create what we call the impact triangle. There are 3 dimensions to understand. First is cost. Most AI services charge you per token processed. Volume equals high API bills. For example, many models charge around 3 cents per 1,000 input tokens. If you can optimize your prompts to use fewer tokens, you directly reduce your bill, sometimes by thousands of dollars a year. Second is speed. More tokens mean higher latency. A typical model processes around 1,000 tokens per second, so a massive prompt takes noticeably longer to return a result. Third is capability. Every model has a hard limit on how many tokens it can see at once. If your document requires 30,000 tokens, but your model only handles 8,000, it simply cannot process the file. The diagnostic rule at the bottom of this slide is crucial. Optimizing prompt efficiency directly shrinks this triangle, dropping infrastructure costs and reducing latency simultaneously.
This brings us to context windows. Think of this as the model's working memory, or its attention span for a single conversation. The definition is straightforward. It's the absolute maximum combined input and output tokens a model can process in a single request. It functions as the strict attention span of the AI for a single, isolated conversation. And here's the hard limit, illustrated perfectly on this slide. If a document requires 60,000 tokens, but your model has an 8,000 token limit, it will instantly fail to process it. The visual shows tokens being fed into a container with a capacity limit. Excess tokens are rejected, shown as the error message in the corner. This is why context window size is one of the first things professionals check when selecting a model.
Context windows are growing at a staggering pace, and this chart shows the arms race. GPT 3.5 Turbo started with just 4,000 tokens, roughly 6 pages. GPT-4 doubled that to 8,000 tokens, about 12 pages.
Then GPT-4 Turbo made a massive leap to 128,000 tokens, around 200 pages of text. And Gemini 1.5 Pro shattered the ceiling with over 1 million tokens, enough for approximately 1,500 pages. The takeaway at the bottom says it all. We have moved from analyzing single emails to analyzing entire code bases and massive libraries in seconds. This is a transformational shift in what AI can process in a single conversation.
However, bigger isn't always better. This slide illustrates a critical phenomenon called lost in the middle. Look at the curve on this chart. The vertical axis shows information recall accuracy, and the horizontal axis shows where information sits in your document. Notice how the curve forms a U shape. Models perform well at recalling information at the very beginning and very end of a large prompt, but accuracy drops dramatically for information buried in the middle. This middle zone is the valley, a high-risk area for hallucinations. The diagnostic fix is on the right side of this slide. Never bury crucial instructions in the middle. Always structure your prompts to put the most critical directives at the very beginning or the very end. This is one of the most practical prompt engineering tips you'll learn in this entire program.
Now, how does a model actually understand what text means? That's where embeddings come in. Embeddings are numerical representations that capture the aboutness of text. They convert language into arrays of numbers that represent semantic meaning. Look at this slide. It shows a three-dimensional vector space with two clusters. On the left, you see the royalty cluster. King, queen, and monarch are all plotted close together because they share semantic meaning. On the right is the fruit cluster. Apple and banana are grouped together. And notice the dashed line between the two clusters, labeled cosine similarity, low. This means the model mathematically knows that royalty and fruit are unrelated concepts. Similar meanings are mapped physically close together in the data, while different concepts are far apart. This spatial relationship is the foundation of how AI understands language. It's important to distinguish LLMs from embeddings. This comparison matrix makes it clear. LLMs predict the next word. Their output is human-readable text. They're slower because they generate token by token. They're expensive, costing dollars per million tokens, and they're best used for creation, reasoning, and summarizing. Embeddings, on the other hand, represent semantic meaning. Their output is vectors, arrays of numbers. They process in milliseconds with instant translation. They cost micropennies, around 0.02 of a cent per 1,000 tokens, and they're best for search, sorting, and duplicate detection. The key insight? Don't use an LLM when all you need is an embedding. Use each tool for what it does best.
This slide shows the real-world problem that embeddings solve beautifully. On the left, you see traditional keyword search. Someone searches for vacation in a company document system. The system looks for the exact word vacation in the company holiday policy, finds 0 results, and fails. Why? Because the document uses the word holiday instead of vacation. On the right, semantic search powered by embeddings. The same search for vacation automatically understands that holiday, trip, and getaway are related concepts. It finds the company holiday policy and returns it as a match. The takeaway is powerful. Embeddings eliminate the need for exact keyword matches. They search by mathematical intent rather than spelling. This is the difference between search that frustrates users and search that actually works.
Embeddings are also the secret sauce behind R, or Retrieval Augmented Generation. This is the technique that makes AI systems accurate and grounded in real data. Look at the 4-step pipeline on this slide. Step 1, embed. You convert your massive document library into a mathematical semantic map using embeddings. Step 2, retrieve. When a user asks a question, you search that map and grab only the 5 most relevant pages. Step 3, load. You feed only those highly relevant pages into the LLM's context window. And step 4, generate. The LLM synthesizes a perfect answer based strictly on the loaded tokens. This is how you analyze a 10 million word library efficiently without hallucinations. The LLM never sees the full library. It only sees the most relevant slices retrieved by embeddings.
Why does RAG matter so much? This slide lays out the 3 pillars of the RAG advantage. First, it beats the context limit. You can process virtually infinite data by only loading what is mathematically relevant at the exact moment it's needed. You're no longer constrained by the size of your context window. Second, it saves the budget. You spend pennies converting data to embeddings instead of burning dollars forcing massive raw token inputs into an LLM. The scale on this slide shows the dramatic cost difference between raw tokens and embeddings. Third, and perhaps most importantly, it stops hallucinations. The LLM is forced to answer based only on the isolated context retrieved from the semantic map, stripping away its imagination. This is how enterprises build AI systems they can actually trust.
To wrap it all up, here's your decision framework for putting these concepts into action. Start by asking, what is the primary objective of your AI task? If you need to generate text, reason, or summarize, use an LLM. Monitor your token volumes and manage the impact triangle we discussed. If you need to analyze massive monolithic documents, use a large context window. But beware the lost-in-the-middle phenomenon and structure your prompts accordingly. And if you need to search, organize, or build a RAG system, use embeddings. Map the meaning, retrieve the data, then generate the final text. So to recap, tokens are your cost and speed units. Context windows are your memory limits. And embeddings are your map of meaning. Now that we know how AI processes text, it's time to look at the engine itself. In our next session, we dive into the transformer architecture and the attention mechanism. I'll see you there.